Hey, good morning, everyone. I hope I'm audible. Can you just put a thumbs up if you can hear me? Perfect, perfect. Hi. Hey, Sailesh. How are you guys doing? Cool. So I'm Arjun. So today's session, the first 2 hours, will be a very basic introduction to graphs. We'll be seeing a bunch of definitions. So the agenda is basically that it's an introduction to someone who is totally new to graphs. And this next two sessions, which will be coming up later in the day, which will be taken by Tanuj, will move more into algorithms on graphs. Whereas in this session, we'll be seeing a bit more theory and not so many. Okay, so Sailesh, I'm not audible. Is that the case with everyone? Can others see me and hear me? Please put a tick. Please put a thumbs up if you can still hear me. Okay, so Sailesh, I think it's an issue with. Maybe you should just try refreshing your page. I think others can. I think I'm audible enough. Cool. So yeah, so that's going to be the agenda. So we'll be looking at graphs, some examples, and a whole lot of definitions. So if you're kind of averse to, yeah, great, Sailesh. So yeah, so it's just going to be a bunch of definitions and some properties, and we'll end with the aim is to end the session with tree traversals, just the basic tree traversal, which will be like probably we'll be doing DFS, and not go into not even implementation details, just give you an idea of DFS, and then Tanuj will start on from that and take up DFS trees from the next session. Yeah. So great. So let's get started. So what are graphs? Vishal, yes, the class is just starting. Maybe try refreshing if you're not able to see this, if you're not able to see the slides. Okay. So before getting into what graphs are, let's look at why we look at graphs. So let's start from great. Yeah, so let's start from a motivation perspective. So I think one easy example to think of, a real life example, is the concept of air network, like flight networks. So just take India. India has a lot of cities and a lot of airports in them. So let's just take, say, four cities for. Sailesh, yes, we'll be coming to all of that in the next 2 hours. Right now, we'll be starting from basics and we'll get to tree traversals towards the end. That we'll be ending with that. So you'll have to be a bit more patient. Yeah. We will definitely get to connected everything. We'll get to all of that. ये किस class के लिए Naman Asan, this is a class meant for introduction to graphs. Yeah, cool. So the example which you can have in mind right now is so just think of all the cities in India, and in particular just take, say, 4 cities. Say we have New Delhi, we have Mumbai, we have Kolkata, and say we have Chennai. Yeah, and we have many flights between them. So we have flights between probably every 2 cities. You can go directly from Mumbai to New Delhi, from New Delhi to Mumbai, New Delhi to Kolkata, and so on and so forth. But this need not always be the case, right? So sometimes maybe there is no direct flight from Chennai to New Delhi. Maybe you can only go through Mumbai, right? So maybe there is a flight from Chennai to Mumbai, and there's a flight from Mumbai to New Delhi, and maybe there's a flight from New Delhi to Kolkata, and maybe there is no other flight, or maybe there is a flight from New Delhi back to Chennai. Yeah. So now if I want to go from Chennai to New Delhi, I need to go to Mumbai and then go to New Delhi, and there is no other way I can do this, right? So, and suppose there are many such cities and there are many such flights, right? And I want to find the shortest, the fewest number of flights I can take to go from one city to another city, right? So I might have to go to multiple cities in between. So when you take the whole world, there are lots of cities, and there are very few direct flights. You'll always have to take indirect flights. So if I want to go from here to, I don't know, some small town in say France, I'll probably have to go from here to New Delhi, and from New Delhi to Paris, and from Paris to some larger city in that region of France, and then from there to the smaller town, something like this, right? So you need to make multiple hops. There might be another way, which is from going from here to, I don't know, London, and then from maybe from Chennai. If I'm in Chennai, maybe I don't need to go to New Delhi. Maybe I can directly go to Chennai. Maybe I can directly go to London, and then from London maybe I can go to Paris. So there are lots of different ways to go to my final destination, and maybe I want to, and I might have various objectives. Maybe my objective is to minimize my time. I want to reach that place as soon as possible. That could be one objective. Another objective could be the cost. Maybe I don't mind spending a lot of time, but I want my cost to be as low as possible. So each flight will have a different cost, right? So different flights have different costs, and they are not always rational. There are lots of discounts, lots of random stuff happening. So the prices can be fluctuating. So maybe a roundabout trip turns out to be cheaper, and this actually in real life happens quite often. So maybe that might be my motivation, and I might want to find the cheapest flight, the cheapest way to go from one place to another. Right? So you see, and maybe at one point, my question is just, can I ever reach that town from where I am? Right? Maybe it's not even possible to go there. Maybe it's never possible to go from one city to another city. It's probably not the case, but you can think of cases where it could happen, right? So these are all different questions which come up in real life, which we want to answer. And if you use these, book my trip and make my trip, these are questions which the systems have to actually answer in real life. When you go and ask, there are multiple various sites which claim to give the best possible deal for you, right? And they often involve such queries. That is, I give my source and I want the destination. I sort it by distance. I sort it by price, right? So, and how are these things calculated, right? And this is where graphs come into the picture. So graph is in essence just a data structure. It is a way to represent things. So it's a model, right? So it abstracts out various data given to you, and you represent it in the form of a graph. There are lots and lots of applications for graphs. But at the core of it, what graphs technically are, you have a bunch of vertices, right? So vertices are like our cities. So each vertex here, so here this is a graph with 4 vertices, yeah, and the flights that we drew between them are called edges, vertices and edges, right? So in essence, in this example we saw, edges are flights and vertices are cities, and edges go from, each flight goes from one city to another. So edges go from one vertex to another vertex, and this is always the case. So edges kind of, you can think of edges as relations between some two vertices. So it's like these two vertices are related. That is, there's a flight between them, so there is an edge between them, right? This is the kind of abstract way you'll have to think about this. So yes, this is basically the crux of a graph. Every graph has its graphs are usually denoted by the letter G. We call it as V comma E, right? Where V represents the vertex set, that is the set of all vertices I'm interested in, and E is the edge set, that is it has all the edges that I want to put into this graph. So we will not name vertices usually as New Delhi or Kolkata or Mumbai. We usually we go with V1, V2, V3, V4. Yeah. Silesh, that is correct. Yeah, we'll get to that as well in a minute. So we'll usually call V1, V2, V3, V4, and the way we represent an edge is something like this. So if there is an edge from V4 to V1, I'll write it as V4 comma V1. This represents an edge from V4 to V1. Similarly, this edge from V2 to V4, I'll write it as V2 comma V4. This is an edge, right? So the vertex set, so when I write G equal to V comma E, V is basically the set V1 comma V2 comma V3 comma V4, yeah, and my edge set is the set of all the edges. So how many edges are there? There are 1, 2, 3, 4 edges, right? So it's the set of all these edges. So it's V4 comma V1, V1 comma V2, V2 comma V4, and New Delhi to Kolkata, which is V2 comma V3, V2 comma V3. Yeah. So this is the set containing all the edges. That is E, which is the edge set. Yeah. Keshav, that's a very good question. We'll come to costs as well in a minute. So right now we're just looking at some basic things. We'll come to all those things one by one. Yeah. So I hope at least the concept of a vertex and an edge are clear so far. Yeah. So let's just draw the same thing again, just more. So sorry. Yeah. So yeah. So we had V1, V2, V3, V4. So this was V1, V2, V3, V4, and we had so this is our usual graph looks like. As Silesh pointed out, this is what we call a directed graph. Okay, so we know what a graph is. What does this directed mean? This directed basically means that the edges are directed. That is, it goes from V4 to V1 and it goes from V1 to V2, right? It's not that just because there's a flight from V4 to V1 doesn't mean there's also a flight from V1 to V4. Okay, so these edges have a direction. So think of in your roads you have one-way roads and two normal roads, and you have one-way roads, right? So these are all one-way roads. I can go from V4 to V1, but I can't go from V1 to V4, right? So this is why these edges have a direction attached to them. So they are directed graphs. Okay, but suppose the flight network is such that all flights, whenever they go, they come back as well, right? So if there is a flight from Chennai to Mumbai, there's also the same flight will return back from Mumbai to Chennai, right? If that is the case, then because this is there, this is also there, because this is there, this is also there, because this is there, this is also there, and because this is there, this is also there. Yeah, everything has, whenever there is one, it's kind of like dual, right? But this of course is a bit weird, right? I mean, yes, there is a flight here and there's a flight here, but isn't a much better representation of the same thing just having V4, V1, V2, V3 and just putting a single edge between them? Yeah, instead of having two edges between every two vertex, which are going in two directions, I'll just put one undirected edge and say this undirected edge means that I can go from V1 to V2 and I can go from V2 to V1. Yeah, so it's like kind of clubbing both this edge and this edge together and making it a single edge like this. Two undirected edges, if you can go from in both directions, we'll just put one single edge and call it an undirected edge, and that signifies that you can go in either direction. So this will be an undirected graph. Okay, Keshav, yes, we'll be discussing Dijkstra. That will be the last session of the day actually. You can look at the schedule that will be covered by Tanuj later in the evening. I'm not sure of the exact time. I think it's probably 4 to 6. Yeah. So this is an undirected graph. Again, undirected graph is just the vertex set is the same. The edge set, just instead of having v1 comma v2, meaning you can go from v1 to v2. Now it will mean I can go from v1 to v2 or from v2 to v1. The direction doesn't matter. Right? So this is an undirected graph. Great. Now, as someone else asked, in the example we gave, we said that we could also look at the costs involved, right? But the graph here doesn't talk anything about graphs. It just says these are connected. I mean, it just gives you the flight. It doesn't give you any information about the flight, right? But if I also want to have information about the flight stored in the graph, that is where we get into the domain of weighted graphs. Okay. Usually what this means is that each edge has a weight attached to it. Okay. So instead of saying I have v1, v2, v3, v4 and I'm basically just going with the same example for all these things right now. Yeah. Instead of just saying that these are the flights, I'm also going to say, okay, this flight costs me 2,000 bucks. This flight costs me 3,000. This flight costs me 4,500, and this costs me, I don't know, 3,500. Yeah. So now this edge from v1 to v2 has a weight of 2,000. Okay. So instead of just writing v1 comma v2, I'll also add 2,000 here. Instead of having just v2 comma v4, I'll have this comma 4,500. Yeah. So these edges now have a weight. Sometimes you could also call this length of an edge, or it's but the usual term we use is weight. Okay. So this weight could have, you could give any significance to it. In this case, the weight of a graph is like the cost of the flight. It could also be the time taken, right? If my objective is to minimize my time, the cost is irrelevant to me. So instead I'll not have 2,000, instead I'll have, I don't know, 60 minutes. This takes, I don't know, 70 minutes and so on and so forth, right? So whatever it is that is relevant for me, I'll put that in the graph, correct? And that will be a weighted graph. And in particular, this is what we call a edge weighted graph. That is, the edges have weights in them, correct? The vertices don't have any weights. The cities, there's no cost to a city, right? It's the cost of the flight between two cities. That is what cost has. So the weights are on top of the edges, and so this is actually called an edge weighted graph. But in general, whenever we say weighted graph, we mean edge weighted graph. So this can usually be ignored. It's just a weighted graph. But what are there different kinds of weighted graphs? Yes, there's also something called a vertex weighted graph. And what is this? As it should be pretty clear, the weights are on the vertices instead of the edges. So each vertex has a weight attached to it. That could also have any significance, right? In which case those will be called vertex weights. You could have a graph in which both the vertices and the vertices, both the edges and the vertices have graphs. That's also totally fine. And those are just usually just called weighted graphs. Yeah, but you'll see later on that these vertex weights can sometimes be just considered as weights on edges, and they're kind of sometimes equivalent in some sense. So in general, most algos that we see will be looking at edge weighted graphs. So whenever you talk about weighted graphs, just think of edge weighted graphs. The edges have some weight in them. And of course, this works even in undirected graphs. It doesn't matter if it's directed or undirected, the edge can have weights. Yeah. So till now, so till now we've seen 4 different kinds of graphs, right? Undirected and unweighted. Undirected and weighted, directed and unweighted, directed and weighted. Yeah. So right now we've seen 4 different types of graphs, and depending on the problem or depending on the data that you want to model, this will change. Whatever you want to use, it's all up to you, right? You're the one who has to make the decision which of these is most relevant for your particular situation. Okay. Cool. Let me just check if there's something on. Cool. So these are in general the most coarse type of classification of graphs. So now we'll get to some more definitions. Okay. So till now the main definitions we've seen are that of vertex and edge. Yeah. So when we say there is an edge, Sanya, sure. Directed graphs are graphs in which the edges have a direction. It goes from U to V or V1 to V2. Whereas in undirected graphs, there is no direction. It's like a two-way road and a one-way road. In an undirected graph, you can travel in either direction. In a directed graph, you can only travel in one single direction. That's the main difference between directed and undirected graphs. Cool. So coming back, when we have an edge between, say, V1 and V3, sometimes we can also name the edges. So maybe this is the edge E1, and maybe I have the second edge, which is some V2 to V3. This is E2, and V3 to V1 is E3, and V3 to V4 is E4. I don't think this is not the same example. I'm kind of changing it, but I'm just saying you can also name these edges and call these the 4 different edges. And why is this useful sometimes? So one terminology we use is that of adjacency, right? So we say that this edge E1 is incident on these 2 vertices. Edge is incident on 2 vertices. Okay, incident is the word. So it just means it's the 2 vertices it is connecting. This edge set is said to be incident on these 2 vertices. So the edge E3 is incident on the vertices V3 and V1. Okay, that is one term you should use. The other term I want to use is adjacency. So adjacency is like neighbors. Okay, so let's go to this graph. Yeah, so we have V1, V2, V3, V4. V1 and V2 have an edge between them. So these 2 vertices are called adjacent vertices. But V1 and V3 don't have a direct edge between them. So these 2 are not adjacent vertices. V1 and V2 adjacent. V1 and V3 not adjacent. Yeah. So similarly, what about V2 and V4? Are they adjacent or not? They are, right? Because there is a direct edge between them. But what about V4 and V3? They are not adjacent because there is no edge here. This edge is not there. So V1 and V4 and V3 are not adjacent in this example. Yeah. So that is the definition of adjacency. 2 vertices are said to be adjacent if there is a direct edge between them. Otherwise, they are not. Cool. So this will become pretty important when we get to something called graph representations, which is how you represent these graphs in your actual program. So we still haven't gotten around to how. Okay, so right now all we are talking about is kind of like abstract, right? How do you tell this to a computer, right? So then there is a different set of things which you need to do. We'll come to that towards the end of the session, and then this will become very important. Okay. Okay. So let's look at the next definition, which is called degree. Okay. So let's go back to the same example. Let's take the undirected graph. Okay. Degree is basically a property of a vertex, and it says the number of edges which are incident on that vertex. Remember the definition of incident from before. So this basically just says how many edges are connected to me. Okay. So degree of V1 will be, there are two edges connected to V1. So degree of V1 is 2. Degree of V2 is how much? Write down in chat, what is the degree of V2? Correct. What is degree? Degree, as we said, is the number of edges connected to V2, right? So there is V2. How many edges are there? This is one edge, this is another edge, this is third edge. So there are 3 edges incident on V2. In other words, how many other vertices are connected to this? V1 is connected to V2, V4 is connected to V2, V3 is connected to V2, all directly connected, right? So the degree of V2 is 3. Degree of V4 is 2, and degree of, so degree can be sometimes shortened to DEG. Degree of V3 is just 1, right? Because there's only one edge connected to V3. So degree of V3 is 1. Okay. So this is the concept of degree when it comes to undirected graphs. Now let's take the same example and turn it into a directed graph. So then let's say these edges have directions attached to them. Okay. So now in the case of directed graphs, we have, we don't usually talk about degree. Instead, we talk about in degree and out degree. Okay. In degree is basically the number of vertices which are coming into my vertex, and out degree is the number of edges which are going away from me. So if I take V4, there is one edge coming into me. It is coming from V2 into V4, right? And there is no other edge coming into V4. So the in degree of V4 is 1. Okay. Similarly, there is one edge going out of V4, and there is no other edge going out of V4. So the out degree of V4 is also 1. Fine. Similarly, let's look at V2. How many edges are coming into V2? There's only one edge coming into V2. From V1, it's coming into V2. There is no edge coming, no other edge coming into V2. So in degree of V2 equals 1, but out degree of V2 is what? What is the out degree of V2? That's correct. Yeah, there are two edges going out of V2, from V2 to V4, from V2 to V3. So the out degree of V2 is 2. Yeah. So in directed graphs, we have the concept of in degree and out degree, whereas in undirected graphs, we just say it's degree. There is no concept of in and out when you talk about directed graphs. Cool. In a while, we'll also look at some properties of these things, but before that, let's look at some other definitions which will be important. Cool. So now we saw edges, right? And we talked about adjacency. So if I have V1, V2, V3, suppose this is my graph. This is a graph with 9 vertices, and how many edges? 1, 2, 3, 4, 5, 6, 7, 8 edges. So there are 9 vertices and 8 edges in this graph. Are V1 and V3 adjacent to each other? V1 and V3, are they adjacent? No, right? Because there is no direct edge between V1 and V3. So you're right. So V1 and V3 are not adjacent. But I can go from V1 to V3 using a sequence of edges. I can start from V1, I can follow this edge to V2, and then from V2 I can follow this edge and go to V3. So when you think of it in terms of flights, maybe I can't go directly from I don't know, Kolkata to Paris, but I can go from Kolkata to Delhi, and from Delhi to Paris I can go, right? So maybe there is, so Kolkata and Paris are not adjacent, but I can reach Paris from Kolkata through some sequence of flights, right? So that is what we call reachability. It is possible to reach V3 starting from V1. So V3 is said to be reachable from V1. There's also another word, V1 and V3 are connected. Okay, so these are kind of like synonyms in a sense, right? This is used in a lot more contexts, which we'll get to in a bit. Right? So V1 and V3 are said to be connected to each other. Right? So when you have so let's just stick to undirected graphs for now. In directed graphs, this will still remain exactly the same. There will not be any difference, right? So in particular, what is reachability? Two vertices are said to be reachable if there is a sequence of edges, right? Such that the edges are next to each other, or rather a sequence of adjacent vertices, right? I can write V1, V2, V3, right? V1 and V2 are adjacent to each other because there's a directed edge. There's a direct edge between them. V2 and V3 are adjacent because there is a direct edge between them. So there is a sequence of vertices, right, such that every consecutive pair is a adjacent pair, and the first vertex, if this is the case, then the first vertex and the last vertex are said to be reachable from each other. So this is like a journey, right? From V1 I go to V2, from V2 I go to V3. Similarly, I can have V1, V4, V6, V3, V5, right? V1, sorry, not V1, V4, V1, V2, V1, V2, V2, V4, V4, V6, V6, V3, V5, V5. So from V1 I can go to V2, from V2 I can go to V4, from V4 I can go to V6, from V6 to V3, from V3 to V5, right? So there's a sequence of vertices such that any two consecutive vertices are adjacent to each other. That is, there is a direct edge between them. And so now this means that starting from V1 I can reach V5. Similarly, I can start from V5 and reach V1 as well. Just because this is an undirected graph, I can go in either direction. So if I can go from one vertex to another vertex, I can also go in the opposite direction. Yeah. So V5 and V1 are reachable from each other in this sense. Now, Sanya will get to that. That's exactly what we're getting to right now. So what we described here is basically what we call a path or a simple path. Okay. So what is a simple path? A simple path is nothing but a sequence of vertices such that every consecutive pair is an adjacent pair, and you don't repeat any vertices. That is, it never makes sense for me to go from V1 to V2, V2 to V4, and then back to V2, and then V5, V3 to V4, right? So repeating vertices doesn't make any sense. When I'm like, even from a real life perspective, when I'm looking at a journey, if I want to go from Mumbai to Paris, why will I go from Mumbai to Chennai, Chennai to Mumbai, Mumbai to Chennai again, and then back to Paris? I'll never repeat vertices. I'll never repeat cities. So that is kind of the intuition behind defining a simple path. So a path is nothing but I want to go from one place to another. It need not be the shortest path. It could be a long path, but I'll never repeat things, right? V1 to V5, this is probably the shorter path, right? V1, V2, V3, V5 is probably the shorter path. But I can take this longer path, but still I don't repeat any vertices. And this is also called a simple path, okay? So vertices and edges don't repeat. If I don't have that constraint, that is, I'm fine with repeating vertices and fine with repeating edges, then we call that a walk. Okay, so walk is nothing but a sequence of vertices. Still, every consecutive pair should be adjacent, but there is no concept of not repeating vertices. I can go from V1 to V2, V2 to V4, V4 to V2 back again, V2 to V1 again, and then I can do whatever I want. I just randomly go from one vertex to another, always just following an edge. The concept of following edges should always be the case. From any place, I can choose any edge going out of me, and I can follow it to the other vertex. And I keep doing this, and I end up somewhere, and that is called a walk. Yeah. Underverb, yes, you can do that. You can have multiple weights in an edge. That's pretty easy to do. There is no issue with that. Siddhant, that is interesting, but not exactly true. So Siddhant is wondering whether graphs are an extended idea of linked list. In essence, you could say linked lists are like a linear thing. Now you can have branches and you can have lots of things. That is one way to look at it, but not a very useful perspective, I would say. But yes, I mean, sure, if it helps you, yeah, you can definitely think of it like that. Okay. So I hope the concept of a path and a walk are clear now. Okay. So now let's go back to that connected term that we talked about. What did we say connected meant? So we said that two vertices u comma v are connected if they are reachable. I mean, we just said that connectedness was a synonym for reachability. So if I can start from u and end at v, or start at v and end at u, whatever it is, in an undirected graph, it doesn't matter. Okay, so maybe before that I should talk about one more thing. So the concept of path and walk will be exactly the same even in a directed graph, except now that you have to follow the walk, you have to follow the edge in that particular direction. I can't go in the opposite direction. Yeah, that's the only thing. So we talked about Siddhant, we haven't gotten to trees yet, but I mean, trees are an undirected graph, but they're an undirected graph with a lot more property to them. We'll get to what those properties are in some time. Okay. So coming to connectedness, so we talked about connectedness of two vertices. U and V we said are connected if there is a path between them. Now we'll talk about connected components. Okay, what does a connected component mean? So let's take some example. Okay, so now V3 and V4 are connected to each other, right? Because I can go from V3 to V1, V1 to V4. Similarly, V3 and V5 are connected, V3 and V1, V3 and V2, V3 and V6 are all connected. But are V3 and V7 connected? No, right? There is no way I can start from V3 and end up at V7. So V3 and V7 are disconnected. correct? I hope that concept is clear. Now, when you talk about connected components, a connected component is nothing but a subset of the vertices such that any two vertices in that subset are connected to each other. Okay. So in particular, in this example, okay, maybe I should take a different color. Yeah. This will be one connected component, and this will be another connected component. Why is this? So I claim that V1, V1, V2, V3, V4, V5, V6, C1 equal to V1, V2, V3, V4, V5, V6, and C2 equals V7, V8, V9. I claim these are two connected components. What does this mean? It means that when I look at C1, that is this connected component, take any two vertices in that. So let's take, I don't know, V2 and V5. There is a path which connects V2 and V5, right? Because I can go from V2 to V4 and V4 to V5, right? Take some other, let's take V4 and V6. V4 and V6 are connected to each other because they are just directly adjacent. It's a even better version for me. Yeah. So in this sense, take any two vertices inside this and they'll be connected to each other. Similarly here, take any two vertices in this set, say V7 and V9, V7, V8, V9, right? V7, V8 or V8, V9. Any two vertices you pick from this and they'll be connected to each other. So if this is the case, then this entire thing is called a connected component. So you might ask, what about the set V1, V2, V4? Yeah, if we just take this smaller set, even in this, you take any two, they're going to be connected to each other, right? V1 and V2 are connected, V1 and V4 are connected, V2 and V4 are connected. So is this also a connected component? Yes, this is also a connected component, but usually we don't consider this to be a connected component, and instead technically this is a connected component, but what we usually talk about are what we call maximally connected components. What it basically means, yes, this is a connected component, but can I expand it and get a larger connected component? Okay, that is it a part of a larger connected component? If it is, then that is what I'm going to look at. I'm going to look at the largest connected components possible, and I'll not be worried about smaller connected components. That is, by smaller I mean things which are inside larger connected components. Like you could also say each vertex is a connected component of itself, right? Because vacuously, there is no way to choose two vertices in a single set, and so vacuously the definition of connected component will hold good, right? But we'll not consider those, and technically everywhere we should say maximally connected components, maximally, but we are just lazy to use that word maximally. So whenever we say connected components, we actually mean maximally connected components, and we actually mean these larger connected components and not the connected components which are included inside them. Okay. So an interesting property is that a graph can always be partitioned into these connected components. So here it's clear that this is one connected component, this is another connected component. If I have some other V10, V11, V12 here, yeah, then this will be another connected component. But suppose there is an edge from V5 to V10, suppose this edge also existed, then all these will be one connected component, this will be another subconnected component. But if I add an edge here, then the entire graph becomes one single connected component. Yes, I hope kind of makes sense so far. Yeah, just put a thumbs up if it's clear till now. That's correct, Siddhant. If all vertices can be accessed from any vertex, then it is a connected component. there are multiple ways you can say this. Any two vertices should be connected to each other, or everything should be connected to one vertex. They're all equivalent ways of saying the same thing. Okay, cool. So these are connected components. Now we can also talk about a graph being connected. So a connected graph is nothing but a graph in which there is one single connected component, which is the entire graph, right? One connected component. That is, take any two vertices in this graph, and those two are connected to each other. Yeah. In this case, the graph is called a connected graph. So with these dotted edges put, this entire graph is a connected graph. If either of these two connected dots are not there, then it is not a connected graph. In particular, this is not a connected graph because there is no way to go from V2 to V7. Yeah. But if this was there, then yes, this entire graph is a connected graph. Got it? Cool. Let me just check YouTube very quickly. Okay, there's something here. Cool. So that is the concept of connected graphs. Now let's talk about some special kinds of graphs. And before that, we look at one particular like it's a feature of a graph, you could say. I don't want to use the word component again. So a cycle, right? A cycle is nothing but it's this, right? It's a loop. It's a circle. It's a cycle, right? So if I can start from V1 and I can get back to V1 again in a without repeating vertices. I shouldn't repeat. I can't go from V1 to V2 to V3 and then back to V2 and then back to V1. This doesn't count. I shouldn't repeat vertices, right? Except the starting. The starting will be kind of repeated because I start and end there. So I can start from V1, go to V2, then to V3, then to V4, then to V5, and then I come back to V1. Yeah. So this forms a cycle. Okay. So there can be other things in the graph. Maybe the graph has V6. Maybe this is a edge. Maybe this is an edge. Whatever it is, I can have a lot of things. Something like this. But still, this what I mark in red is a cycle in this graph. Yeah, Keshav, I think that's exactly what I've said. Yes, even if V2 and V5 or V1 and V4 are connected, this is still a cycle. So the term you are looking for is a induced cycle. Okay. So I'll not. So the question you asked is basically the definition of this. An induced cycle is a cycle which doesn't have these internal chords. Okay. But I'll not get into details of that. Just Google induced cycle and you'll get the answer to that. Yeah. You're basically asking for a kind of like a stronger version of a cycle, which I don't want to introduce right now, but that's basically what it is. Cool. So coming back, so this V1, V2, V3, V4, V5, V1 is a cycle no matter what else is there in the graph. I don't care about anything else. These things are there, so this is a cycle, right? If a graph doesn't have any cycles, it is called a acyclic graph. Okay. So, and a cyclic graph is just a graph which has a cycle. Yeah. So why are cycles important? So we'll see some properties of these down the line. In particular, when we come to trees, this will become pretty evident why acyclic matters a lot. In a very small, like, hand wavy thing, cycles often cause issues. Cycles are the reason for a lot of headaches in graph theory. So if a graph doesn't have cycles, we are a lot of things become very nice. Okay. So it just becomes an easy problem most often when the graph doesn't have cycles in them. This will probably become clearer to you in the next few sessions as well. Okay, so but we'll not get there right now. So the definition of cycle is this. Cool. So now let's look at some special kinds of graphs. Okay. So if I have a graph which is like this, okay, I have 3 vertices and 3 edges like this, right? Is there any other possible edge here? No, right? There is no other edge I can add. These are the only 3 possible edges, and I've added all of them. Similarly, let's take another another graph, right? And I try to add all the possible edges. So from V2, these are the 3 edges possible, right? From V1, there's already 1 edge. This is another edge I can add. This is another edge I can add, right? From V3, this edge already exists. This edge already exists. This edge I'm adding. From V4, this and this, all 3 of them already exist, right? So now what I've gotten is 4 vertices and 1, 2, 3, 4, 5, 6 edges. Yeah. So 4 vertices and 6 edges. And now, is there any other edge you can add in this undirected graph? No, right? All possible edges we've added here. And this is what we call a complete graph. So it is a graph with n vertices and nc2 edges. That is, take every 2 vertex and add an edge between them. In any edge possible, put it in the graph. So it's like you're completing the graph, right? There is no more edge you can add. You add everything. And what is going to be the number of edges? It's going to be n into n minus 1 by 2, right? nc2. The number of ways of choosing 2 elements from n elements is n into n minus 1 by 2. And that's going to be the number of edges. I hope this is clear to everyone. Losing life, that's true. These 3 vertices do make a cycle. Yes. Yeah. So this is a complete graph, and in a complete graph, the number of sorry, one second. Yeah. So in a complete graph, the number of edges is always nc2. And just to be clear, we are only talking about undirected graphs. In a directed graph, you'll have to have every 2 edges. That's not usually done. We usually talk in terms of undirected graphs. Cool. One more kind of trivial graph is just a cycle. If the graph has nothing but one single cycle, that is, I have only V1, V2, something like this, right? Or it could just be V1, V2, V3, or V5, right? And there are no other edges. I can't have an edge between V1, V2 and V4. I can't have a V5 edge like this. Nothing else. The entire graph is just this one single cycle, and it's just called a cycle graph. Note the difference between cycle and cyclic graph. A cyclic graph has a cycle. A cycle graph has only a cycle. Okay, so a cycle graph is a cyclic graph, but a cyclic graph need not be a cycle graph. Okay. So this is both a cycle graph and a cyclic graph, whereas this graph is a cyclic graph, but it is not a cycle graph, right? Because it's not just a cycle, there are other things in the cycle apart from the cycle as well. So it is not a cycle graph, but it contains a cycle, so it is a cyclic graph. Okay. So just to be clear, all cycle graphs are cyclic because they contain a cycle, so it's also cyclic. But not all cyclic graphs need to be a cycle graph, right? I hope this is clear. Good. So this is cycle graph. Another kind of trivial graph is what we call a path graph, which is nothing but a single path and nothing else, right? So it's usually V1, V2, V3, V4, V5 and nothing else. There are no edges between them. There are no V2, V4 edges. There is nothing V2, V6, nothing else is there. It's just one single path and nothing else. And this is what we call a path graph. Am I missing something else here? I think that's mostly it. We'll get to bipartite in a few. Okay, maybe I'll just do bipartite right now. A bipartite graph is a graph where the vertices can be split into two sets, right? So usually we have G equal to V comma E, right? Now this V, I can write it as V1 union V2. Keshav, that's not true. Not acyclic graphs are trees. I'll give you, we'll get to that in a bit. Ask me that question when we come to trees. We'll actually cover that. Okay. So coming back to bipartite graph, G equal to V comma E, and V I can write it as, so this, do you know what disjoint union? Okay, for now let's just think of it as V1 union V2, where V1 and V2 are disjoint of each other, right? So my vertex set, I can think of it as V1 and V2, such that, so V1 has some vertices, V2 has some other vertices, such that all the edges are only between V1 and V2. So I can have lots of edges like this. Okay, but I can never have an edge between two vertices in the same partition. Okay, if this basically, amongst all the vertices here, there are no edges between them. Amongst all the vertices here, there are no edges between them. Between these two, there can be edges. In this case, this is said to be a bipartite graph. It's basically bi is 2, right? So I kind of partition it into 2. So that's bipartite, and my edges are between them. Similarly, I can have a tripartite, which is basically 3 and this, but then that's not usually done. Bipartite is what we usually get to. Maybe right here I should talk about two other, a few other definitions as well. So let's get to subgraphs. Okay. What is a subgraph? A subgraph is just a subset of the vertices. So I have some vertices, I take a subset of the vertices and a subset of the edges, such that the edges are only within these vertices. Okay, so if I have V1, V2, V3, V4, V5, V6 and V7, then if I just take these vertices, then I'm taking the subset V1, V2, V3, V4, then this is a subgraph, and a subset of the edges as well. So, and the subset of the edges should be only within these vertices. So I can't, if I take only v1, v2, v3 and v4, I can't take v5, v7 as an edge, because that doesn't lie inside this, right? So I can only take amongst these 4 edges, I can take any of these edges, and that will be called a subgraph. So subgraph is a subset of the vertices and a subset of the edges, such that all the edges I choose are only amongst the vertices I've chosen. Yeah. So it's like taking some edges, and amongst them, so some vertices, and amongst them, whatever edges are there, I take some of them. And another definition is an induced subgraph. An induced subgraph is just a subset of the vertices, and all the edges between them I have to take. Okay. So if I have, if these are my vertices, and v1, v2, v3, v4, v5, v6, v7, and suppose my induced subgraph takes the vertices, I don't know, v1, v2, v3, v5 and v7. Yeah, so I'm basically picking v1, v2, v3, v5 and v7. So what will the induced subgraph be? So I'll write v1, v2, v3, v4 I'm not writing, v5, v6 I'm not writing, v7, and now all the edges which lie between them. So this is an edge, this is an edge, and this is an edge, right? So I'm taking all the edges which lie between these vertices, and this is called an induced subgraph, right? So a subgraph is just, this is a normal subgraph. Maybe I don't take this edge as well. Maybe I don't take this edge. Those are all subgraphs, but an induced subgraph is take all the possible edges. That's called an induced subgraph. Okay. So path graph we go. Okay, that's a very, very good question. Keshav, you're absolutely right. So Keshav is basically asking, is a path graph a bipartite graph? That's absolutely correct, because let's go back and see. So a path graph was like this, and a path graph can be thought of as a bipartite graph, because I can take v1, v3, v5, so maybe there is v6 as well, and v2, v4, v6. So I have v1, v2, v2, v3, v3, v4, v4, v5, v5, v6. So this is a partition such that all the edges only go between them. There is nothing inside either of these two partitions. So a path graph is always a bipartite graph. That's absolutely correct. Okay. A very nice observation, Keshav. Okay, so now that we are here, so we know that a path graph is always bipartite. Okay, we just proved this. What about the other special graph we saw, a cycle graph? Is a cycle graph always bipartite? So is this a bipartite graph? Is v1, v2, v3, v4 a bipartite graph? Okay, Sanya says yes. What about the rest? Okay, Varad also thinks this is a bipartite graph. Okay, correct. So why is this a bipartite graph? I can just take v1, v3, v2, v4 and say v1 to v2, v2 to v3, v3 to v4, v4 to v1. Yeah. So I have I've partitioned my vertex set into two paths, and all the edges go only between them and not amongst them. So this is a bipartite graph. So can I say that a cycle graph is always a bipartite graph? So a path graph is always a bipartite graph. So is a cycle graph always a bipartite graph? Okay, Keshav says no. Why do you think so, Keshav? What about the rest? So we just saw that this is a bipartite graph. Okay. Why do you think so, Bharat? No, Bharat, that's why I said it's a cycle graph, not a cyclic graph. So in a cycle graph, there is no other edge. The only edges are those in the cycle. So all the edges are involved in the cycle. There is no other edge in the graph. That is what we call a cycle graph. Okay, so Bharat thinks a cycle graph will always be a bipartite graph. Okay. Okay, so Shobit thinks that it's not always a bipartite graph, and he's given a example which he says will be counter example. What about the rest of you? What do others think? Will a cycle graph always be a bipartite graph? Okay, Gaurav also thinks it's yes. Okay. Okay. Cool. So actually, Keshav and Shobit are correct. The example we saw, yes, this is a bipartite graph, correct. But it is not true for all cycle graphs. In particular, just take the cycle graph with 3 vertices. Yeah. V1 has to be, say V1 is in this. So I need to partition it into 2 things. And say I put V1 here. Okay. If V1 is here, because V1, V2 is an edge, V2 can't be here, so V2 should be in this side. So let's put V2 here, right? Similarly, V1, V3 is an edge, so V3 can't be this side. So V3 also should be on the right hand side. So let's put V3 also here. But now V2 and V3 have an edge, so there's an edge between this, right? So we get a contradiction, no? So this is not a bipartite graph. Yeah. In particular, whenever there are an even number of edges, the cycle will be a bipartite cycle. But an odd number of edges will not be bipartite. Okay. Why is that? It's just basically V1 has to be this side, V2 has to be this side, V3 has to be this side, V4 has to be this side, V5, V6. If I end here, right, then the edge between V6 and V1 and V6 are in different sides. So if it's even number of vertices, my starting and ending are in different sides. So the final edge will go across and it's bipartite. But if I have one more, V7, yeah, now V1 and V7 are in the same side. And so they can't have, the edge will not make it bipartite. So even number of edges, even number of vertices, and it's the same as edges as well, will be bipartite. Odd, not bipartite. Okay. So very good question, Keshav. So a path graph is always bipartite, but a cycle graph may be bipartite or not, depending on the parity, even odd, of the number of vertices. Cool. Yeah, Bharat, that's exactly correct. I hope this made sense to everyone. Okay. So let me just have a look at. Okay, there's nothing. Oh, wait, my bad. Okay. Cool. So I hope that made sense to everyone. So we had a look at connected graph, subgraph. Okay. So let's look at another definition, which is called a clique. So what is a clique? A clique is basically an induced subgraph of a graph, which is like a complete graph. So if I have sorry, yeah. So now the entire graph is not a complete graph, right? So remember, what is a complete graph? A complete graph is a graph in which all the possible edges are present. So this is obviously not a complete graph because say v1, v2 itself is not an edge, yeah. But consider the subgraph, or consider this induced subgraph which has only the vertices v2, v3 and v4, yeah. This and this. Now what is the induced subgraph? The induced subgraph is just this triangle v2, v3, v4, and this is a complete graph, right? So every possible thing is present here. So if an induced subgraph which is a complete graph is called a clique. So v2, v3, v4 forms a clique of this entire graph. Okay. So let's take this as well. Yeah, suppose these edges are all there. Maybe there is v6, v7. Yeah. Now these four vertices v2, v3, v4, v5, they form a clique because there are four vertices such that inside them all the six edges, possible edges, are present. So this subset of vertices is called a clique. Why? If I take all the edges, then it forms a complete graph. The induced subgraph on those vertices forms a complete graph. So v2, v3, v4, v5 is a clique. Okay. Next, we'll move to the concept of independent set. Okay. So let's take the same example, v1. Okay, maybe not same example. I'll try to give say for now these things. Let's consider the vertices v1, v4 and v6. Okay, the set v1, v4, v6 is called an independent set because take any two vertices from this set. Yeah, v1, v4. Are v1 and v4 adjacent? No. Sideways exactly. Yeah. v1 and v4 don't have an edge between them. Similarly, v1 and v6 don't have an edge between them. v4 and v6 don't have an edge between them. Right? So take any two vertices from this set. There is no edge between them. They might be connected, but they are not adjacent to each other. So such a set is called an independent set. There is no edge between these guys. Okay. Can you give me another example of an independent set in this graph? v2, v5. Exactly. Yeah. So v2, v5 is another independent set. v3, v5. I could have v1, v5. That is also an independent set. v3, v4, v6 is an independent set. Exactly. Right. So all these are independent sets. So one classical problem is to find the size of the largest independent set in a graph. So given a graph, in this case, I can't have an independent set of more than size 3. You can easily see that. But in general, just finding the size of the largest independent set is a classical problem which is very hard to do. That is just called the maximum independent set size, maximum independent set problem. And it's a pretty hard problem to solve. we'll not even get to it today, but just giving you a heads up. So now let's go back to bipartite graphs. So now do you see that V1 is basically an independent set and V2 is also an independent set, right? Because this is a set of vertices such that amongst any two of them there is no edge, and similarly this is a set of vertices such that amongst any two of them there is no edge. So the definition of bipartite graph, now that we know the definition of independent set, we can rephrase it as any graph which can be partitioned into two independent sets is a bipartite graph, because I have this set, this is an independent set, this is an independent set. Inside this there are no edges, inside this there are no edges, and there can be edges between them that I don't say anything about. So this becomes a bipartite graph, right? So cool, just a different way of defining a bipartite graph. It's exactly the same, just because we know this definition, we came back and revisited this, right? Cool. So now let's go back to degrees, and I said that there was some property of degrees that we'll get back to, right? And that is what we call handshake lemma. This is a very interesting, cute property. Okay, what it basically says is take any undirected graph, right? Say V1, V2, V3. Okay, and list down the degrees of all these vertices. What is the degree of V1? It's 2. What is the degree of V2? It's 2. What is the degree of V3? It's 2. What is the degree of V4? It's 3. And what is the degree of V5? It's 1. Okay, and add up all of these. Basically take the sum of all the degrees. So 2 plus 2 is 4, 6, 9, 10. Yeah, and this 10 is basically 2 into 5, where 5 is the number of edges. How many edges are there? There are 1, 2, 3, 4, 5 edges. Yeah, so it is 2 into 5, and this is going to be true no matter what graph you take. In particular, the handshake lemma says that the summation of degrees is 2 into number of edges. Okay, so let's just take one more example, just a small example, say V1, V2, V3. Yeah, what is the degree of V1? It's 2. What is the degree of V2? It's 1. What is the degree of V3? It's 1. So the summation is 4, and 4 is 2 into 2, where 2 is the number of edges. Yeah, you can take any more examples and it will always be true. It's a very cute property, right? They seem pretty I don't know, very far apart concepts, degrees and number of edges. Why should this be true? It's actually not that hard to prove this. It's basically every edge contributes. We'll also get to this exact formula is true only for undirected graphs. There is a version of this for directed graphs which we'll come to in a bit. Okay. So for now we are only looking at undirected graphs, and I basically just want to convince you why this is true. So when I take this edge V2, V4, right, what did it do? It basically added a degree of 1 to V2 and added a degree of 1 to V4. Right? So it contributed a sum of 2 to the left hand side. Right? So basically all I'm saying is think of this 2 as 1 plus 1, this 2 as 1 plus 1, this 2 as 1 plus 1, this 3 as 1 plus 1 plus 1, and this 1 as 1. Right? So the summation is basically the number of ones here. So when I take V1, V2, I'm saying it contributed this one and this one. Yeah, v3 contributed, sorry, this edge contributed to v1 and v3, so it contributed this and this. v4, this edge contributed to v4 and v5, so it contributed to this and this. Yeah, so every edge contributed 1 to the degree of 2 vertices. So when I add all the degrees, I'm basically going to, how many ever edges were there, I'm going to each edge, I'm going to count it twice. It's going to contribute 2 to the sum. So the sum of all the degrees is nothing but 2 into m, 2 into number of edges. Okay, just to be clear, so number of edges will often be called m, the number of vertices will often be called n. It is a common protocol that we use in a lot of places. Right. So summation of degree of vi over all I is 2m or 2e, whatever it is. I hope, it is a very, very hand-wavy proof, but this can be made very rigorous very easily. But I hope you're convinced of why this is true. And the reason why this is called a handshake lemma is basically, okay, this is not exactly the handshake lemma. The handshake lemma is that the summation of degrees is always even. I think that is what the exact lemma says. And that is also pretty easy to see, right? Because the summation of the degrees, by the same logic, each time when you think of an edge as handshaking between the people, and you add up all the people, you're in a party and there are lots of people and some of them shake hands, and for each person you count the number of people that person shook hands with and you add all of these up. So it'll always be even, because each time I shook hands with someone else shook with me, so it contributes 2. It's the same principle. Each edge contributes 2 to the sum of degrees, and so when I add everything up, it's an even number because it's 2 plus 2 plus 2 many times. So it's going to be an even number, and in particular, it's basically just going to be 2 into number of edges, which is exactly this. So did this make sense? Put a thumbs up or a thumbs down if you understood or didn't understand this. Great. Okay, I don't see any thumbs down. So good. So this is, I think, the first non-trivial property that we've seen so far. And this surprisingly becomes, it's a very simple fact, it's surprisingly very useful in a lot of places. Hopefully you'll see something later in the evening, I'm not sure. Okay. So cool. So, okay. So then I think we'll now come to the concept of distances and shortest distances, shortest path. Okay. So we'll still remain in the realm of unweighted graphs, and we'll get to weighted graphs in a minute. Okay. So what is the shortest distance in an unweighted graph? Let's stick with undirected. Directed also will be the same. There's not much difference. Suppose this is the graph that we have, okay? And suppose I want to find the distance between V1 and V5. So the distance is nothing but the number of edges I have to travel to reach V5 from V1. So the shortest distance is going to be to go to V2 to V4 to V6. That is, I travel 3 edges. So distance of V1 comma V5 is 3. So note that I could have taken a longer path. I can go from V1 to V3, V3 to V7, V7 to V4, V4 to V5. So I'll travel 1, 2, 3, 4 edges. But that is not the shortest distance. The shortest distance is to go like this. So the shortest distance is what we denote by D. So D of V1 comma V5 is the number of edges I have to travel to reach the smallest number of edges I have to travel to go from V1 to V5, and in this case it's going to be 3. What is going to be D of V7 comma V2? It's 2, right? Because I can go from V7 to V4 to V2, so I travel 2 edges. Yeah, I could have also gone like this, but that would take 3 edges, and it's a longer path which I don't want. So this is the distance. In a disconnected graph, that is a graph which is not connected. So if I have say V8 and V9 here, then what is the distance of V1 comma V9? No, it's not 0. It's actually infinity. Yeah, it's -1, or we in like mathematical terms we just say it's infinity, because there is, I mean, it's so large that I can't even travel. It doesn't make sense. But usually you'll define it as infinity, because if it's 0 is like going from myself to myself. Distance of V1 comma V1 is 0, because I can start from V1, end at V1 by traversing 0 edges. Yeah, but I can't start from V1 and end at V9 by traversing 0 edges. It's just not possible to reach. So it's either -1 or infinity. -1 is like a flag we use. Yeah, so this is, but usually you'll talk about distances only in connected graphs, so you don't need to worry about this usually. Okay. And now let's put in the concept of weights. Okay. Now if all these edges have weights, so maybe this has 10, 20, 5, 2, 1, 4 and 3. Now what is the distance between V1 and V4? So now distance is not going to be the number of edges, but rather the sum of the weights along the path. Okay. So now if I take V1, V2, V4, my distance is going to be 10 plus 20, which is going to be 30. Okay. But that is not the shortest path. What is the shortest path? The shortest path is to go to V3 to V7 to V4, because then my shortest path length is going to be 5 plus 2 plus 1, which is going to be 8, right? And as Sailesh said, that is the shortest path. Even though the number of edges I'm traveling is larger, the sum of the weights is smaller, right? So think again in terms of flights. To go from Chennai to some town in Paris, maybe it's better to make many flights which are cheaper rather than one direct flight which is super costly. Yeah, so this might be a cheaper option, and that is what we are looking at here. Okay, so this is the shortest distance, and the shortest path is this and not this. Keshav, that's right. If the weights are not given, then we consider the edge weights to be 1. Yeah, and that gives us exactly what we did earlier. And now the shortest distances and shortest path have a huge kind of chapter on their own. There are lots of algos to find the shortest path in various different scenarios. When there are weights, when there are no weights, when they're directed, undirected, when there are negative weights. Do you want to find the distance from one vertex to everything else, or do you want to find the distance between every two vertices? Lots of questions, and Tanuj will be looking at least one of those later in the evening, and there are some more also as well, which you'll see later on if you join something else. Yeah. Yeah. So Saurav, this Tanuj will be covering implementation of. In particular, there is one algo called the Dijkstra's algo, which helps you find the shortest distance between one vertex and every other vertex. Okay, so from V1, I want to find the shortest path to everything else. That you can do fast enough. And Tanuj will be covering the entire algo and the implementation of that, I think, in the 4 o'clock to 6 o'clock session. Okay. Sailesh, probably not. I don't think we'll be, maybe DFS, I'm not even sure. Mostly just of a theory class. No. Okay. So this is distances. So today will we see how to implement graph? Yes, sort of, definitely, yeah. The basics, yes, we'll do, but implementation of Dijkstra, Tanuj will be looking at it. Okay. Cool. So I think now we have covered most things, and now we can move to trees. Whereas I think Tanuj will try to do it language agnostic. So I think it shouldn't matter whether you know C++ or Java. but if at all he's doing proper coding, I think he'll do C++, but I'm sure he'll give you links to Java implementations as well, so don't worry about that. Okay. So now we come to the next important concept, which is called a tree. What is a tree? A tree is nothing but a special graph, and in particular it is an acyclic graph, which is also connected. Let's remind ourselves of the definition of acyclic. What is acyclic? Just a graph in which there are no cycles, right? And what is connected? A connected graph is a graph in which any two vertices have a path between them, right? So usually a tree will basically look like this. This is an example of a tree. Is it acyclic? Yes, there are no cycles, right? You can't start from V2 and get back to V2 without repeating vertices. You can't start from anything and get back. There are no cycles anywhere. And is it connected? Yes, it is connected, right? Take any two vertices, V2 and V5, there is a path between them. Yeah, V8 and V7, there is a path between them, right? Any two vertices in this graph are connected. Okay. Case of I'm not sure about implementation. Basically depends on the amount of time we have. Anyway, we'll give you some codes which you can look up later. Don't worry about that. We'll look at definitely the way to represent these things, but exact code I'm not very sure about it. It depends on time, how fast we go. N-ary tree we'll not get into that as well, Sailesh. It's just a general tree for now. Don't think of what exact kind of tree it is. It's not an n-ary tree to be precise. So is the definition clear? It is acyclic and it is connected. Suppose I had an edge like this. Now you see that this is not, it is still connected, but it is not acyclic, because now V2, V1, V2, V3 becomes a cycle, right? So that will not be a tree. Similarly, if I have V10, V11, V12, now these 12 vertices are still acyclic. There is no cycle anywhere, but they are no longer connected, right? So this is also not a tree, and this is actually called a forest. So this is a nice, this is I think the best definition in all of computer science that I like. So forest is nothing but a collection of trees, right? A forest has lots of trees in it. So this is a forest because this is a tree, and this is just these three vertices form a tree, because these are connected and this is acyclic, so it's a tree. These are connected and these are acyclic, so this is a tree. But these are two different trees put together, they form a forest. Okay, so a forest is a collection of trees. But this entire thing is not a tree. That's I think someone had this exact question before, whether acyclic implies tree. No, acyclic does not imply tree, because this is an acyclic graph, but it is not a tree because it is not connected. So acyclic implies a forest. Acyclic unconnected implies a tree. Okay, great. So this is one definition of a tree. There are actually lots and lots of definitions of tree which are all equivalent. You can prove that all these different definitions are equivalent to each other. We'll look at some definitions. Keshav, yes, there can be a forest with a single tree. Yes. In other words, a single tree is also a forest. A tree is always a forest, but a forest is not always a tree. Yeah. Cool. So let's look at some properties of a tree. So a tree by definition is acyclic, there are no cycles, and it is connected. Another important property is that the number of edges is always 1 minus the number of vertices. Okay, that is m equals n minus 1. So let's forget this. There are 9 vertices in this tree, and what are the number of edges? It's 1, 2, 3, 4, 5, 6, 7, 8. Okay, there are 8 edges in this tree with 9 vertices, and this is going to be true always. Okay, so why is this the case? This can also be proved not so. It's pretty easy to prove. So I'll just try to give some, at least an intuitive reason why this is true. So whenever you think of a tree, it's always easy to think of a rooted tree. Okay, so first let's see what a rooted tree is and a non-rooted tree is. So this is a tree, right? It is acyclic and it is connected, but sorry. Yeah, but it's a kind of like a vague thing. So what we'll do is we'll root the tree at some point. What that basically means is pick some vertex. It can be any vertex. You can pick any vertex to be the root. Let's say I pick v4 to be the root. Okay, so what that means is that I'm going to take v4 and write it at the top. Okay, then I'm going to take all the edges going out of v4 and put it down. How many edges are there going out of? The degree of v4 is 3, right? So from v4 I have v2, I have v5, and I have v6. Now v5 and v6 don't have anything else adjacent to them, but v2 has 2 more vertices, v1 and v3. So I'll put them beneath v1 and v3. Yeah. So now this is a rooted. So these two are exactly the same. There's no difference between this picture and this picture, right? All the vertices and all the edges are exactly the same, except that I've drawn it in a different way, right? I've drawn it as I've basically taken one vertex and think of it as like, imagine that you can kind of in your head just imagine like pinching that vertex and putting it on top, and imagine now there's gravity, so everything falls down, right? So there is this root and the edges next to it, and the edges next to them are below, and so on and so forth, right? So it's like rooting the tree on this vertex is basically what we've done here. This is a rooted vertex, rooted tree, and this is an unrooted tree. So this is the root. Vinod, no, there is no necessity that we have to pick a node with maximum out degree. There's no such. I can root it on v1, and let's just do that. So if I root it on v1, I'll get v1, I'll get v2, v3, and v4, and beneath v4 I'll have v5 and v6. That is also a perfectly valid rooted tree. Okay, so that's rooted trees. And so now when we talk about rooted trees, so whenever you talk about a tree, it's always, even if there is actually no explicit root, usually in all problems and all scenarios, it's totally fine to imagine any arbitrary root, and so that you have this nice structure like this. And why is this structure nice? Because now we can talk about some specific terms called, so we can talk about basically up and down, right? There's a concept of something above me and something beneath me, right? So there is v4, and v2, v5, v6 are just beneath me, and these are what we call children. Okay, v2, v5 and v6 are children of v4, v1 and v3 are children of v2, v5 doesn't have any children, v6 doesn't have any children. And the converse, we also have parent. v2's parent is v4, v5's parent is v4, v6's parent is v4, v1's parent is v2, v3's parent is v2. Okay, so parent is the vertex just above me, and children are all the vertices beneath me. And it should be clear that every vertex has a single parent except the root. The root doesn't have anything above itself, so there is no parent to the root. but every other vertex has a unique root. Sorry, has a unique parent, right? It should be clear that a vertex can't have two parents, right? If V3 has V2 and suppose this is also there, then this forms a cycle, right? So a vertex can't have two parents. It can have exactly one parent, except the root, which has no parents. Okay, I hope it's clear till now. So this is a very crucial property of trees, right? Children and parents. And we also have the concept of depth. Depth is basically the distance from the root. So this is at depth 0. All these three are at depth 1. And suppose there is also V7 here. All these three will be at depth 2. It's basically the level from the top that they are at. The further down, the further away from the root they are, and the deeper they are in the tree. So you can think of your family tree. So at the top you have, I don't know, some great grandparent, and then their siblings, and then their children, and then children, and children, so on and so forth. Yeah. So this is a tree, child, parent, and depth. Okay. Is there any questions so far? Is everything clear? Just put a thumbs up if everything is clear so far. Cool. Okay. What do we want to do next? Yes. So we were talking about the fact that the number of edges in a tree is always n minus 1, right? So why is that the case? So now think of a rooted tree, right? So I have say something like this. Now what we observe is that every edge goes between a child and a parent, right? This edge goes from this child to its parent. This edge goes from V5 to its parent. This edge goes from V6 to its parent, and so on and so forth, right? So every edge goes from a vertex to its parent, except the root, because the root doesn't have any parent. Okay, so the number of edges is just n minus 1. That is, forget the root, every other vertex an edge to its parent, and that's basically the number of edges. So m equal to n minus 1. It's a very, very hand-wavy proof, but I hope it kind of makes sense to everyone. Right? Every edge in a tree can be thought of as going from the lower node to its parent, right? And so every node except the root has an edge going up, and these are all the edges there are no more edges in the tree, because if there are any more edges you get a cycle, which is bad, which will no longer be a tree. So the number of edges is exactly n minus 1. Okay, and so this is actually a more kind of like a general property as well. In any connected graph with n vertices, if you have more than n minus 1 vertices, you'll always have a cycle. This is also something you can prove. Okay, so I'll leave that as an homework. So just I'll repeat it. In any connected graph with n vertices, if there are greater than n minus 1, that is greater equal to n edges, there'll always be a cycle. This is something you can try at home to prove, and that's it's often a very useful thing to know. Okay, so I think we are mostly done with these as well. Next we'll move to graph representations. That is, okay, we've seen all these graphs and everything is all abstract, and in our head it all makes sense, but how exactly do you go and convert this and code it in a so that a computer understands things? So the first thing to do for any of this is to first understand how to represent a graph in a computer, right? And this basically has two main methods. One is called the adjacency matrix, and the other is called the adjacency list. Okay, so let's first look at the adjacency matrix. So let's forget this for now. Let's just look at adjacency matrix. Let's take an undirected, unweighted graph. Yeah, so I have V1. Suppose this is my graph, right? So the adjacency matrix corresponding to this will be a 4 cross 4 matrix. A matrix is nothing but a 2D array, right? It's 1, 2, 3, 4, 1, 2, 3, 4. And wherever there is an edge between 1 and 2, right? So it's V1 and V2 is a 1. Similarly, I can go from V1 to V2. There's an edge from V1 to V2, right? In a sense. Or maybe for now let's think of it as directed edges. Maybe that will be easier to understand. Let's this. Let's take a directed unweighted graph. Okay. So now there is an edge from V1 to V2. Okay. So 1, 2 will be a 1. There's an edge from V2 to V3. So 2, 3 will be a 1. There's an edge from V3 to V4. So 3, 4 will be a 1. There's an edge from V4 to V2. So 4, 2 will be a 1. And everything else will be a 0. So this is the adjacency matrix corresponding to this graph. So if there is an edge from U to V, then A of UV equals 1. Otherwise, it is equal to 0, where A is the 2D adjacency matrix. Is this clear enough? No questions? That's it. It's a very simple way to represent a graph. So any graph I have, if I have n vertices, I'm going to declare a 2D matrix of size n cross n, right? Or maybe n plus 1 cross n plus 1 if you want to go with 1 based indexing and not 0 based indexing. And then for every edge which is from U to V, I'll initialize everything to 0 first because there are no edges. Then every time an edge comes which is U to V, I'll make A of UV equal to 1, which means there is an edge from U to V. Okay. Now sometime later in the code, if I want to know whether there is an edge from V3 to V1, I don't know. I want to ask whether it's possible to have an edge from V3 to V1, whether it exists or not. So all I'll do is I'll look at A of 3, 1. If it is 1, yes, there is an edge from 3 to 1, V3 to V1. If it's 0, there is no edge from V3 to V1. Right? That's it. Over. What exactly do you mean by sparse matrix, Gaurav? Are you saying the number of ones is going to be fewer and like less dense, that kind of sparse? That need not always be the case, right? Like think of a complete graph where every two things has an edge between them, in which case there will be ones everywhere. Right? The entire matrix will be filled with ones. So it need not be the case that it's a sparse matrix. There are various definitions, but I hope you understand what I'm saying. The number of ones need not be small. It could be the matrix could be filled with ones. Yeah. Cool. Yeah. So Sailesh, insertion of an edge is basically whenever an edge U, V comes, just do A of UV equal to 1. Just put that line in your code. A of UV equal to 1. That goes and changes the matrix value to 1. If I want to delete an edge, if there is an edge U to V and I want to delete it, I'll just do A of UV equal to 0. So it's no longer an edge. It's as simple as that. Or if a new vertex comes, okay, new vertex is going to be, let's just say it's impossible for now. I mean, you could like kind of resize your 2D matrix and do something, but that's way too complicated. You should always, you can't handle vertex. You should know the number of vertices at the beginning, and that's how you declare a 2D matrix and then do on. You can't handle vertex, new vertex addition or deletion. Deletion is also to some extent, I guess, easy because you could just make the entire thing 0 and 0. But let's not go into that. We'll just talk about edge addition and deletion. Yeah. Cool. So now when we go for undirected graphs, so this was a directed graph. If it's an undirected graph, and we think of undirected graph as basically two edges, v1, v2. So let's just remove these directions now. So now it's not just v1 to v2, but also v2 to v1, right? So it's not just this is 1, this is also 1. It's not just v2 to v3, so it's not just 2, 3, but also 3, 2. This is also 1. Similarly, it's not just this, it's not just v4 to v2, but also v2 to v4. So 2, 4 is also 1. Similarly, it's not just 3 to 4, so it's not just 3, 4, but also 4, 3. This is also 1. Yeah. So now basically, whenever an edge u, v comes, it's both a of uv equal to 1 and also a of vu equal to 1. That's correct. You put 1 in both a of v1, v2 and v2, a of v2, v1. Yeah. So now this is, you'll basically get what is called a symmetric matrix. A symmetric matrix is a matrix where a of ij equal to a of ji for all I and j, and that's going to be true for this. Okay, because that's exactly how you define things. Because if I can go, if there's an edge from u to v, there's also an edge from v to u, because it's an undirected edge, and it's an undirected edge and an undirected graph. Yeah. So this is basically an adjacency matrix. So what is nice about this? In constant time, you can know whether an edge exists or not. Edge exists, or you can also add an edge or delete an edge, everything. Yeah. But what is bad about this? The bad part is that you need to spend order n square space. Yeah. You need a 2D matrix, so it's n square space, right? So that's a bad thing. Another bad thing is if I want to find all the neighbors of a vertex, right? That is, if I want to find all the vertices which are adjacent to v2, right? So for that, what should I do? I should go to the second row and scan everywhere and find where all one is there, right? So even if a vertex has only 3 neighbors, I still have to spend order n time to find all neighbors of a vertex. Yeah, because I have to go through that entire row and see what all are adjacent to v, which is kind of bad because I mean ideally I only want to spend degree of v time. Yeah? If v has 3 neighbors, if I can find those 3 neighbors in 3 time and not spend n time, I'm happy. Yeah. So these are the 2 cons, bad disadvantages of adjacency matrix. And to solve these 2 disadvantages is what the next representation comes, which is adjacency list. Okay. So let's take the same example, v1, v2, v3, v4. And let's just take the undirected setting. Okay. So an adjacency list for this is basically going to be 4 lists. Okay. So let's call this B of 1, B of 2, B of 3, B of 4. So B of 1 is going to store all the neighbors of 1. What are the neighbors of 1? It's just 2. B of 2 is going to store all the neighbors of 2. What are the neighbors of 2? It's 1, 3 and 4. Neighbors of 3 are 2 and 4. Neighbors of 4 are 2 and 3. And this is my adjacency list. Okay, so it's basically n different lists. Yeah, it's n different lists where the ith list contains all the neighbors of the ith vertex. Okay, so now this is not going to take n squared space because it's going to take only as much space as there are number of edges, or rather 2 into number of edges. Because, so do you see that the size of the ith vertex, size of the ith list is basically going to be the degree of I. If there are I neighbors, there are going to be I elements in this list, so it's going to be degree of I. So summation of all this is going to be summation of all the degrees, which if you remember from the handshake lemma is nothing but 2 into m. So space from n square, which was adjacency matrix, we've now brought it down to order of m. In particular, it's 2m, which is order of m. Yeah. So space has reduced a lot. So if, in particular, if my graph is sparse, so what is a sparse graph? A sparse graph is a graph where the number of edges is not n square, or rather n choose 2. The maximum number of edges is n choose 2, right? In a complete graph, there are n choose 2 vertices. Sorry, n choose 2 edges. That's like n square. So it's not like n square, maybe it's like n, or maybe 2n or 3n or even n root n, right? It's asymptotically lesser than the maximum number of edges. So that's usually what we call a sparse graph. Usually it's like linear, like n is what usually happens. So in which case the space, the space efficiency is a lot. We've gained a lot of space efficiency by using adjacency list. And the other con, which is to find all the neighbors of V. Also now I can find in degree of I time because I just go through this list. I don't need to spend n time each time. I just go over this. If I want to find all the neighbors of 2, I just go over this list and I find exactly the neighbors of 2. I don't need to go through people who are not my neighbors. Yeah, so that both the cons of adjacency matrix are solved here. But of course, this also comes with its own disadvantage, right? So in particular, in an adjacency matrix, if I wanted to find whether there's an edge between u and v, I could do it in constant time. I just look at a of uv. If it's a 1, there's an edge, otherwise it's not an edge. But here it's not so simple, right? If I want to find whether there's an edge from u to v, I have to go to b of u and I have to look at that entire list and find whether v exists in that list or not, right? I could make this somewhat better by maybe sorting this list and doing a binary search. But still, it's even then it's going to be log of degree, which worst case it's log of n time. It's not constant time. It's at least log n time in this case. Yeah. So that is one issue. Similarly, deletion also I need to find and then delete it. So deletion is also an issue. Yeah. Deletion could also be as bad as log n, or even it depends on how you. It's a bit more complicated. Let's not go there. Usually you won't do deletions in these things. But what about the important addition, right? Addition is not so bad because why? When an edge u comma v comes, what do we need to do? I need to go to b of u and plug in v into this. Yeah, so it's just, if I don't care about sorting property, I just shove in v at the end. Similarly, I go to b of v and I shove in u at the end. So if you're doing C++, you'll basically just keep these as vectors, right? So the size doesn't matter. It's a dynamic array, right? At the beginning, you don't want to declare the whole array because then that would defeat the purpose of saving space. Yeah. So it's a dynamic array, and at the end, whenever an edge u comma v comes, you add v to the adjacency list of u, and you add u to the adjacency list of v, and that's it. That takes care of everything. But the main thing to note is that if you do this, it will not be sorted. So checking whether an edge u comma v exists or not is not going to be log n, it's going to be order n because you have to go through the entire list. So that's one drawback. So there are lots of kind of tug of wars happening here, different various things. So whatever it is that you need to optimize, you'll need to be careful about it and figure out exactly what method works for you. So in particular, adjacency lists you will see are very useful in DFS, which actually we don't have time to get into now. So Tanuj will start with DFS, and you'll see that adjacency lists are critical for DFS because you will want to look at all the people who are adjacent to you. This particular, even though it kind of feels like a slightly unnatural query than just asking whether u comma v exists or not. That seems like a more natural question to ask, right? But in fact, in practice, this is the question you need to ask very often. So a lot of places, this is what you'll want to optimize rather than just asking whether a single edge exists or not. So usually you'll prefer using adjacency list over adjacency matrix. But of course, there are situations where you have to use an adjacency matrix as well. And the adjacency matrix are often easier as well than adjacency lists. So if both are possible, you'll probably go for adjacency matrix. But there are some cases where you definitely have to use adjacency list to get your to get your efficiency proper. Yeah. And one such example is DFS, which you'll see in the very next session. Okay. So cool. So that wraps up our graph representations, which are basically adjacency matrix and adjacency list. Okay, and the pros and cons of both. So just a few implementation details when you're using C++ or Java for that matter. Adjacency matrix is simply just a 2D matrix. There's no issue with that. Adjacency list will be an array of vectors in C++, and I believe it's pretty much the same in Java. Instead of vectors, you have a different thing, lists or something. I'm not exactly sure. Yeah, so basically a dynamic array. Array lists, I think it's called. Don't take what I'm saying for Java very clearly. It's basically a dynamic array, whatever it's called in Java. Yeah, and you just keep adding things at the end to get your to get the adjacency list of each vertex differently. Yeah. So cool. So let's wrap it up here. We've gone past our time. I hope you learned something. So the next coming 2 sessions, I think it'll be probably more fast-paced than this because I tried to go a bit slow this time. Tanuj will probably have to go a bit faster than what I did, and yeah. So please stick around. Hopefully you'll. I forgot. Sorry. I need to also. Yeah. Sorry. So coming to the Unacademy part. So this was just a special class. So we have structured courses like this going on in Unacademy, and in particular from 22nd December we have a batch starting which will cover exactly what we did. So graphs will be one of the first topics, one of the main topics you'll be covering. I think there are 2 separate courses as well for graphs, and yeah, so it's like a proper structured learning where we go through all of these in different courses. So there are different durations as well. And the instructors, we have some very, very good instructors taking these things up. The IOITC, ICPC World Finalists, Red CF people. And yeah, so you also get these CodeChef certification free at the end of your 6-month or 1-month course. So it used to be called CCD SAP if you're familiar with that. So it's like a certification it's an exam which you can give. And hopefully you'll pass it if you go through the course properly. It should not be much of an issue to get the certification if you are attentive enough in all the classes and do the things. The expense, it comes to $90 per day. Yeah. So you get interactive classes. So it's exactly like this. This will be exactly the format. You'll have, but in addition to that, you have a lot of practice problems. You have teaching assistants who will be helping you out with very quick responses, not just during the class, even away from the class. There's a Discord server where people answer very quickly, and the teaching assistants are also amazing people who are, I think, some red coders and like people with very, very good credibility. And then this is the exact structure. Yeah, I'm not sure what exactly the color coding is. Okay. Okay, the color coding is okay. So forget the colors. Colors are a bit weirded out. So it's basically you start from very basic programming, which is like flow charts, and then if you're not familiar with the if you're not familiar with the language, it also goes through that. And so it's like a 52-week, it's a entire 1-year program. But there's also I think the batch starting from 22nd is actually it's an intermediate batch, so it'll actually start from we'll start from sorting search. No, sorry. Yeah, where will it be start from? Yeah, it'll start from greedy algos and sorting, searching, and things. It'll not you'll not learn about flowcharts because I'm assuming a lot of you already know those parts. So it'll start from the intermediate part alone. Yeah. And yeah, so these are the educators. I mean, you have some really amazing. Like yeah, so Tanuj will be taking the next 2 sessions. He's a 2-time world finalist, IOI, and Google, Facebook, everything. Like yeah, all these are like really amazing people around here. Yeah, here in this page alone you have 3 world finalists, Google, multiple Facebooks, Flipkart. Yeah, and I'll also be taking some courses in between. Yeah, and you have teaching assistant support on Discuss and on Discord as well. Yeah, practice problems, and this is your this is the pricing plan, which comes to $90 per day. You can use this CodeChef to get, I believe, a 10% discount, if I'm not wrong. So please do use that. Cool. I think that wraps it up, and hope you got something out of it. And do stick around for Tanuj's class. You'll definitely enjoy Tanuj's lectures. If you got something out of this, I'm sure you'll get a lot out of Tanuj's classes. Yeah. See you. Bye.